So let us recall what we have did in the previous lecture. In the previous lecture, we have defined a cycle. A cycle is a non-trivial tail in a graph G if the origin and the internal vertices are distinct. Then it is called cycle. We know that the cycle is denoted by Cn of it if it has n distinct vertices. Then we have seen certain results on cycles. We have seen very important results that a graph which is a bipartite, if and only if it has no odd cycle. Afterwards, we have defined the Euler tool and Hamiltonian path. So what is the Euler tour? The Euler tour of a graph G is a tour which includes every edges of the graph G exactly once. Now what does it mean of Euler, or what does it mean of a tour? A tour is a and if the graph contains Euler tour, then that graph is known as Euler graph, or it is an Eulerian graph. And we have seen certain examples of Euler graph and Eulerian graph, and there is a very important results to check whether the given graph is Euler graph or not. For that, you have a theorem. It's called the Euler's theorem, which tells you that a connected graph is a Euclidean graph, or I can say Euler graph, if and only if every vertex has an even degree. There is another one more result is there which you want to find out whether the given graph has Euler tail. A connected graph has an Euler tail if and only if it has at most two vertices of odd degree. Then we have discussed regarding the Hamiltonian path. A Hamiltonian path in a graph G is a path which includes every vertex of the G. Then we have discussed regarding the Hamiltonian cycle. A Hamiltonian cycle in a graph G is a cycle which includes every vertex of a G. And a graph is known as a Hamiltonian graph if it is contained Hamiltonian cycle. So with this, we have also defined a complement and a self-complement of a graph. Hope you have understood in the previous lecture, and also we have discussed regarding the trees. So a tree is actually a cyclic connected graph. Acyclic means a graph which does not have a cycle. Then we have discussed regarding the forest. So forest is actually a collection of a tree. In short, I can say, or in the definition, if you can say a forest is a acyclic graph. It is disconnected acyclic graph. Okay. And then we have seen certain results on or some certain properties of a binary tree. So what is the definition of a binary tree? Is a tree in which exactly one vertex of a degree 2 and each other vertices of degree 1 or 3, it's called the binary tree. And we have seen certain results on this binary tree. Here we'll discuss certain more results on a binary tree. So that I'm discussing the first one as a theorem is that every pair of vertices in a tree is connected by one and only one path. So it says that in a tree, every pair of vertices will connect by only one and only path. There is always one path is there. What will happen if it has two paths? So that is the way we can prove this result. So let T be a tree, and in this tree, let's say A and B are arbitrary pair of vertices. Now, since they are the arbitrary pair of vertices and a T is a tree, so it is a connected graph. What is the definition of a tree? It says that it is a connected acyclic graph. So since T is connected, there exists a path between A and B is there, because A and B are connected. Connected means there exists a path in between A and B. Okay. So since T is connected, graph A and B are connected by a path. So they are connected by a path. What is we have to prove? That it is only one and only one path is there. Let us assume that if possible, A and B connected by two distinct paths. Then what will happen in a tree? Can somebody tell me? So there is a tree is there. Let's say this is the tree, and this tree is might be situation is of the tree is like this. We don't know how this tree is growing. Okay. Suppose this is the tree, maybe, and it may be extended on this side, maybe extended on this side. We don't know. But let's say this is A, and this point is B. Now what happened? What is this? What we have assumed that A and B are connected by two distinct paths. So there one path is I can see, that is one path is here. So it has, as per our argument, there has to be another path is there, which join this A and B. So let's say this is the path is there. Then what will happen? Then what should happen?
So we have a cycle.
In that case, we have a cycle. See, one is this. So joining these two paths will contain a cycle. And what is our assumption? In the hypothesis is given that the T is a tree. A tree is acyclic connected graph. So T does not contain a cycle. So that's why this is a contradiction. Why we got a contradiction? Because we have assumed that it is two distinct paths. What should I write these two paths? Together form cycle, and then T cannot be tree. So what does it mean? That means that therefore there is only one path possible containing A and B. So only one path is possible containing A and B. The converse is the converse of this result is true. How you can state the converse? If there is only one path between every pair of vertices in a G, then can you say that G is a tree? Is the converse of this result is true? Let me state, yeah, that is also true. The theorem is like this. If there is one and only one path between every pair of vertices in a graph G, then G is a tree. See, first of all, if you want to prove that G is a tree, that means you have to prove that it is a cyclic connected graph. So why it is connected? Can somebody give me argument that why this G is connected? If G has every pair of vertices are connected by one and only one path. Because what is the definition of a connected graph? The definition of a connected graph says that every pair of vertices are connected. That means every pair has a path in between them. Here it's saying that one more thing, that is one and only one path is there. So that means this argument tells you that the G is connected. Okay. So existence of path between every pair of vertices ensure that G is connected. Why? It is a tree. We need to prove it is a tree. So why it will be acyclic? Connected we already done. Now we have to prove that it is acyclic graph. So let us assume that it has a cycle. Okay, so if possible, G possess a cycle. If it is possess the cycle, then there exists, because what will happen in a cycle, if you have a cycle, okay, then what will happen if you consider any two pair of vertices in this cycle, then there will be the one path is this, another path is this via this one, and one more path is there, but our assumptions tells you that there is only one and only one path. So if it is possible there is a cycle, then there exists at least one pair of vertices A and B, say A and B, such that there are two distinct paths between A and B. So there are two distinct paths between A and B, which we can say. And this contradict the statement or hypothesis. The hypothesis is so G does not have a cycle. Okay, hence G is tree because it is connected, which we already did, and it is tree. So ultimately, what we can say is every tree, if it is there, if and only if every pair of vertices is connect via one and only one path. Okay. One more result we can see here regarding this tree is a connected graph is a tree if and only if what will be the things? If the graph is a tree and it is a connected graph, so suppose that tree is there. Okay. An addition of age, if you put any age in between any two vertices of the graph G will create a circle. Is it? So if I put, suppose this is a tree, and if I join this one and this one via one edge, then what will happen? It will form one cycle.
Cycle.
Yeah. So that is the result. A is connected graph is a tree if and only if an addition of an edge between any two vertices in a graph creates cycle or circuit also I can say create cycle, but precisely I can say creates exactly one cycle. So it will create one cycle in between this. We'll not discuss the proof of this, but you can see this is very important result. Now the next question I can ask you, then if tree with n vertices, a tree has n vertices, then how many number of edges tree has? For example, here we have a tree. This is the tree we have. How many so this tree has 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, n is equal to 9. So what is the number of edges which I am denoting maybe n? E. 1, 2, 3, 4, 5, 6, 7, 8. It will be 8.
N minus 1.
Yeah, you plot any of the tree and count how many number of edges a tree has. So you are right what you are saying, that a tree with n vertices has n minus 1 edges. Okay, and this result one can prove using mathematical induction. We're not discussing the proof, but one can easily prove that using mathematical induction. Whether the converse of this result is true, how I can state a converse of this? A connected graph with n vertices and n minus 1 edges. Is it a tree? So that is also a theorem is true. So the theorem is says that connected graph with n vertices and n minus 1 edges is a tree. We have discussed regarding the definition of minimally connected graph. Minimally connected graph means what? A connected graph is said to be minimally connected if a graph becomes disconnected when you remove one edge from it. That is called minimally connected graph. What about what you can say about the tree? A tree is a minimally connected graph. And any graph is minimally connected. Can you say it is a tree? That are the two questions I am asking you. I'm repeating the question. A minimal connected graph means what? If you remove one edge from the graph, from the connected graph, and a graph will become disconnected, then that is called, that graph it's called the minimally connected graph. Now I'm asking you a question. You have a tree. Can you say that it is a minimally connected graph?
A tree can be a minimal graph, but a minimal cannot, maybe or may not be a tree.
The converse. That means a minimally connected graph is a tree. It is both the way the result is true. That means a graph is a tree if and only if it is minimally connected. Okay. And there are lots of other results on this tree you can state and you can discuss them. But limitation of a time, I'm not doing all the results. A next definition is very important, is known as a spanning tree. So what is the definition of a spanning tree? A tree, it's called the spanning tree of a connected graph. First of all, it has to be a subgraph of G and it contains all its vertices. So I'm writing a tree T, it's called a spanning tree of a connected graph G. If T is a subgraph of G and if T contains all the vertices of G. Okay. So many times this finding the spanning tree in a graph G is very important questions. For example, I can give you an example that suppose there is one warehouse and from the warehouse there are certain shops are there and we have to give we have to supply a goods to each and every SOP. So we have to find out. So there are certain rules. Many routes are possible, joining warehouses and shops. If you want to travel a goods with minimum cost, that means you have to visit each and every shop, and also you have to, your cost should be minimum. So that means you have to visit every vertices. So if I consider that shop as each and every vertices, so I need to find out one spanning tree with joining, which has exist in the graph G. So that is the major application of finding the spanning tree in a graph G. So in other words, a spanning tree is also known as a spanning subgraph, which is a tree. If you have recall your definition of a spanning subgraph, spanning subgraph is a subgraph in which the vertex sets is same. So spanning tree of G is a spanning subgraph of G that is a tree. The next definition is a branch of a tree. A branch of a tree is any edge of a tree. It's called a branch of a tree. An edge of a tree, it's called branch of a tree. For example, let me give you example of this spanning tree. Suppose my graph is this. This is my graph G, and if I denote the edges of that one with A, B, C, D, E, F, G, and H. This is not a vertex. Now, what will be the spanning tree of this? So there are many spanning trees are possible. The first one I can say it is, if I starting with this vertex, then it is, this will have A. Then you come back here, this is the C. When you go here, this will be F, and this will be H. So all the vertices are covered in this, and this is a tree. So this is a tree, and this is a spanning tree. Example of a spanning tree. Okay. And this A, C, F, H, all of them I can say it is the branch of a tree. Now there is a definition of a chord of a tree. A chord of a tree is an edge. The edge of G that is not in T. It's called a chord of T in G. For example, in this D is the edge which is not in this tree. So I can say this D is a chord of a graph or chord of the tree. So here, for example, G is a chord of a tree in G. A next definition is a co-tree. A complement of a spanning tree in a connected graph G, it's called the co-tree of a graph G. So co-tree is the complement of a spanning tree in a connected graph G. It's called co-tree of T, and it is denoted by T bar. For example, this is my spanning tree. So what is the complement of this tree in this graph? That is known as a co-tree. So I'll put the co-tree here, that is denoted as T bar. So in this graph, what you can have, this edge is there, but this one is not there. Obviously, the vertices remain same. The vertices should be same in the T and in T bar. But this edge is here, so this edge is not here, so that's come here. C is here, E is not there, then G is there, then F is there, H is there, D is not there. So this is the a co-tree of the graph G. Okay. If the graph contains a spanning tree, then what you can say about, what is the property of the spanning tree, you can say. I'm repeating the question. If you found that a spanning tree in a graph G, then what you can say about the G? Is it connected graph or it is disconnected graph?
Connected graph.
Yeah, connected graph, because a spanning tree is contains all the vertices. Okay, and it is a tree, so that means there exists a path between every pair of vertices, as per our discussion above. So that means a spanning tree, sorry, any graph G has a spanning tree, then it is connected. Is the converse true? That means a connected graph have always a spanning tree. If a graph is connected, then can you find a spanning tree in it? So that is also true, and we can state a result like a graph G has a spanning tree if and only if G is connected. So this is the results on a spanning tree, we can say. The another result is, let T be a spanning tree in a connected graph G, and you know that G has n vertices and E edges. then T has space number of branches. What do you mean by branches? We have defined a branch of a T. Branch is nothing but the edge of the T. So how many edges are there? And space number of chords. We have defined a chords. A chord of a tree is the edge which are not exist in T. That is known as a chord. So can somebody fill these two blanks? That if T is a graph, or sorry, T is a spanning tree of a graph G, and it has n vertices and e number of edges, then how many number of branches are there? In other words, how many number of edges are there? So we have just before few minutes we have proved that if T is a tree, then this many number of edges will be there with n vertices.
N minus 1.
So here this G has n vertices. So this T is also having the n vertices because T is a spanning tree. So that's my this T has n minus 1 branches. Now how many number of chords will be there? What is the definition of a chord? Those edges which are not exist in T. So total number of edges will be E.
E minus n minus 1.
N minus 1. So that is E minus n plus 1. That many number of chords will be there. Okay. Fine. Now the next definition is a fundamental cycle, or many times it's known as a circuit. So a circuit is formed by adding a chord to a spanning tree of a graph G. It's called the fundamental circuit. Okay, what I'm saying, a circuit or a cycle. By adding a chord to a spanning tree of a graph G, it's called fundamental cycle or circuit of a graph G with respect to that spanning tree, whatever the spanning tree you have found. For example, I can give you an example. Suppose this is the graph you have. Suppose this is the graph G, and in that these are the vertices A, B, C, D, E, F, and G. These are the vertices. Now, first of all, you have to find out the spanning tree of this graph G. To get a fundamental circuit, first you should have a spanning tree of this. So if I start with A, then let me consider from A to B, then B to C, C to F. You can consider this side or you can have this side, okay, whatever you like. Let me go with this D, and then you will go to G, and then come back to F, E. So this is my spanning tree. Now what is the definition of a chord? To get a fundamental circuit, you have to add one chord into it. Okay, one chord means the edges which are not exist in spanning tree, but it is in G. So let me draw this one again here. So this is my A, B, C, F. This is D, G, and E. And if I draw this, any edge, you can put any edge in between any two vertices, which are here. It has to be here in the graph G, but not in this. Then I'm adding this edge here. Now this is known as, or so what is the fundamental circuit? You have E, G, D, B, C, F, and again E. You will come back. It is known as fundamental cycle. This is known as a fundamental cycle. Find the fundamental circuit for the graph this, what I'm plotting here. V1, V2, V3, V4, V5, V6, and V7. Find the fundamental circuit in this. Okay, so that is your task to do it. So first objective is to calculate what is the fundamental. What is the spanning tree in this graph, and then calculate the fundamental circuit. Should I leave this to you guys? That finding the fundamental circuit in this, can you able to do that? Yes or no?
Yes, sir.
Yeah. So let's stop for today now, because the next topic that I'm going to teach you is regarding the algorithms on graph to find out the shortest paths algorithms, and we'll discuss few algorithms to find out the shortest path, few algorithms to find out the spanning trees in a graph, and that's it for this. Okay, so let me stop for today here. If you have any question, you can ask.